Greetings to everyone. My name is Chinmay Vinay Dandavati. I am a student at the MSc Statistics program, semester 1, in the Institute of Science, Nagpur. And the topic which I have been allotted for the presentation for the seminar of the topic of distribution theory is Weibull distribution. Before I start with my topic, that is Weibull distribution, I would like to begin with a very fundamental question. What is a distribution? So in order to find out the answer for this question, let me start with an example. Let us consider that we are having a few people and our task is to measure their heights and to put them into certain bins as per their heights. So we can see that we have these bins. We can see that the leftmost bin is for the people who are having height less than 5 feet. The rightmost bin is for the people who are having height more than 6 feet. And these two bins, these are for the people who are having their height between 5 feet to 5 feet 6 inches and between 5 feet 6 inches to 6 feet respectively. So now what we do is we start measuring the heights of the people and we start placing them into the bins which suit their height. So we start with this. We start placing the people into the bins. So here now our exercise is finished. All the people, their heights are measured and they are placed into these bins. So the thing which can be observed is that if any person who does not know about these bins is made to randomly choose a person, then there is a good chance that it would be between 5 feet to 6 feet, since majority of the observations are in between two bins. Now we will continue the same activity, but we will do a change. The change would be that we will reduce the width of the bin by 50%. That is, the bin which is 6 inches of width right now will become of width 3 inches. So now we have 4 bins. Now we will take 8 bins. These are the heights. So now these bins are half as wide as they were previously. Now the width is of 3 inches, earlier it was of 6 inches. Now we again start placing the people, the same bunch of people, into these bins. Again, most of the measurements as they were previously are between 5 feet to 6 feet. But now we can be more precise and we can say that half of the people are between 5 feet 3 inches to 5 feet 9 inches. That is these two bins. We can see these two bins, these have the majority of people. So now we extend this activity. We keep increasing the number of people. We keep decreasing the width of the bins. And at a certain arbitrary stage, we get a distribution like this. Now here you can see that we have a stack of people. Now these are not people, these are, let's say, random variables in the language of statistics. So here it can be seen that these are the stacks of random variables, which can be termed as histograms. So now what we do is that we take a curve like this and we try to join these random variables with the limits, and we can use a curve to approximate this histogram. But now we can observe that here there is a gap. Here there is no random variable. Perhaps the people who selected the lot of those human beings for measurement of height So there was no one who was having a height which could be placed into the bin which was present over here. But now if we generalize this entire situation, so since we can't calculate the probability with the histogram, does that mean that we will never get a measurement that fits into this bin? So the answer is no. In fact, this curve which we have drawn very recently, which we have constructed very recently, would be good for the calculation of probability. Now, one more thing. I said that we have been reducing the width of those bins. Earlier it was 6 inches, then it became of 3 inches and so on. But in case I have to calculate the probability of any person to have a height between a very small interval, an interval which is having a difference of a very few decimal places. So in such case, this curve makes sure that we are not limited by the width of the bins. If we want to find out the probability of measuring someone between say 5.021 to 5.317 feet, we can easily do so by using calculus or by using computer without having to round up to the nearest bin. So now that we have observed both the histogram, that is the stack of these balls or random variables alternatively, and this curve, these are the distributions. They show us as to how the probabilities of measurements are distributed, and they represent the mathematical law in accordance to which the different values of the random variables are distributed with a specified probability of each variable. Now this is called as a distribution. This is the answer to our question that this is a distribution. So also one more thing, that the peak of this curve or the tallest part of this histogram shows the region where the measurements are most likely. So now we have been talking about how height measurements are distributed. But there are all kinds of distributions with all kinds of interesting shapes, and one of it is Weibull distribution. So the Weibull distribution is one of the most widely used distribution, and it's a continuous distribution. It is a versatile distribution that takes on the characteristics of other types of distributions based on the value of the shape parameter. The Weibull distribution is named after the Swedish professor Valody Weibull. It is a generalization of the exponential distribution which has the PMF theta e to the power minus theta x, where theta is the parameter of the exponential distribution, and it is used for the lifetime data analysis and is appropriate for a system having several constituent parts. Now let me focus on this last point. It is said that this distribution is used for lifetime data analysis and is appropriate for a system having several constituent parts. So what is so much special in this distribution that it is used in this lifetime data analysis, or it is used in a system which is having several constituent parts? So the thing which needs to be known, that Weibull distribution is also called as a distribution which calculates the time or the duration of failure, the duration after which a certain part or certain object can fail. And thus this unique property of this Weibull distribution denotes its applicabilities or its scope in various fields, and we can get it that it is used in reliability engineering, medical research and climatology. Now why reliability engineering? So let's say we are making some construction, some architectural model, or anything for that matter, any infrastructure, any building. So if I am using a certain material for designing that building, so up till what time will that material last? At what time has that material maximum probability to stop working or to perish? That can be found out by Weibull distribution. Medical research, in medical research, I think it has the highest application, especially in cardiology. Now, in case there are some people whose heart is not working properly, let's say, so they are given with this pacemaker, a device which is applied in the heart and which helps the heart to function very well. So now if the pacemaker is made up of certain material So at what time has that pacemaker maximum probability to stop working? This needs to be known beforehand, because before that expected time, that pacemaker can be replaced with a new one and the person's life can be saved. Now the third field, climatology. Now climatology, the highest application of this climatology is in farms, agriculture. The time at which the maximum rainfall is expected, at that time the farmers are not supposed to sow the seeds so that their efforts can be saved from being wasted. So time to failure data, such as the probability that a part fails after 1, 2 or more years, can be determined by using this distribution. The constituents of this distribution are these three parameters, that is the shape, which is denoted by the symbol beta, the scale, which is denoted by the symbol eta, and the threshold parameters or location, which is denoted by the symbol gamma. Now the PDF of Weibull distribution is given by f of t, which is equals to beta by eta, whole bracket t minus gamma upon eta, whole to the power beta minus 1, e to the power minus t minus gamma upon eta whole to the power beta, provided f of t is greater than or equal to 0, for t is greater than equal to 0, or gamma or beta is equals to greater than 0, eta is greater than 0, provided gamma lies between minus infinity to infinity. Now generally the threshold of the parameter is set to 0, and thus the PDF which we have seen previously gets converted into a two parameter Weibull distribution, which has a PDF as f of t equals to beta upon eta into t upon eta whole to the power beta minus 1 into e to the power minus t upon eta whole to the power beta. And one more thing which needs to be known is that this distribution is defined only for non-negative variables. So now we will start studying each of the parameters separately and what is its effect, the net effect in determining the PDF of the Weibull distribution. So we will start with the effect of the shape parameter, that is beta. So shape parameter or beta, it is also known as the Weibull slope. The value of beta is the slope of line in the probability plot. So as you can see, the value of beta equals to 3 approximates a normal curve. The value of beta between 2 and 4 is still approximately normal. Low value of beta, let's say 1.25, gives a very right skewed curve, and high value of beta, that is 10, gives a left skewed curve. So now, what is a Weibull probability plot? Now this Weibull probability plot shows how the slope of the Weibull probability changes with beta. Hence the shape is also the slope. Now the shape of the parameter characteristics are beta equals to 1 for exponential distribution where the object concerned has a constant failure rate. For beta equals to 3.5, it's a normal distribution, it's an approximation. For beta, which is less than 1, there is a decreasing failure or a hazard rate, and for beta, which is greater than 1, there is increasing failure or hazard rate. This can be described very well by this diagram, where we have these graphs, how these graphs are running. As I have said, beta equals to 1 has a line which makes 45-degree angle with both x and y axis, and it passes perfectly through the origin of this graph, and there is a constant failure rate. For beta equals to 3.5, or here we have 3, so we can see that it's a normal distribution and it's an approximation actually. For beta equals to 0.5, which is less than 1, it is a decreasing failure rate. It can go in this direction. So what is the effect of the second parameter, that is the scale parameter? Now scale, or the characteristic life, is the 63.2 percentile of the data. Now a change in the scale parameter has the same effect on the distribution as a change of the abscissa scale. Now eta, as it is the symbol of the scale parameter, has the same unit as t, time, such as hours, miles, cycles, actuations, anything. Now it defines the Weibul's curve relation to the threshold, which is analogous to the way the mean defines the position of the normal curve. A scale of 10 indicates that 63.2% of the equipment will fail in the first 10 hours after the threshold time. Now what is this threshold time? Threshold time is the time till which everything will function very smoothly without any failure or without any obstacle or a fault. Now the increasing value of eta with beta constant has the effect of stretching out the probability distribution function. Now what are the effects of the threshold parameter? Now previously we have seen what is threshold parameter. Now we have to see what are the effects of the threshold parameter. The threshold is a shift of the distribution away from 0. A negative threshold shifts the distribution to the left of 0, whereas a positive threshold shifts the distribution to the right of 0. Now what does this mean in a metaphorical or in a practical sense? Now if I use a material which is way too substandard. Now let's say if I am supposed to make a building, or leave alone a building, if I am supposed to make a bridge. Now for making that bridge I am using metal pillars. Now it won't be a single metal, obviously it would be an alloy. So let's say the alloy is absolutely substandard. It has lot many contaminations, lot many impurities. It is below the bar. So the probability of threshold will be to the left of 0, that is it would be less than 0, which means that if in case the bridge is supposed to sustain for say 10 years, it will sustain only for 5 years. After 5 years it can collapse at any time. Now in case I am very much sincere and very much honest in making the bridge, I use an alloy which is say 100% pure. I use the best smelting techniques. I use the best cement. I use the best men. I make sure everything is top notch. So now the threshold shifts to the distribution right of the distribution of 0. That is, if the bridge is supposed to sustain for say 10 years as it was supposed to previously, now it might sustain for 15 years or 20 years. So this is the meaning of this negative and the positive threshold. So now third point, all the data must be greater than the threshold. That is beta or alpha, it should be greater than threshold. Now Weibull distribution is an alternative to the normal distribution, as we have seen previously in our previous graph, in case of a skewed data. In this graph, again as we have seen earlier, y has the same units as t. Now here we can see time versus time. This is a function of time which also has the same unit as time, and we can see this graph. So now generally the threshold parameter is set to 0. Thus we have this 2-parameter Weibull distribution which is defined as f of t equals to beta upon eta multiplied by t upon eta whole to the power beta minus 1 e to the power minus t upon eta whole to the power beta, which is defined only for non-negative variables. Now a 2-parameter Weibull distribution with parameters 4 and 100 is exactly the same as a 3-parameter Weibull distribution with parameters 400 and 30, except for the 3-parameter Weibull is shifted to 30 units to the right of 0. That is, if this is say the threshold is 30, it is made sure that the entire scale of the distribution now is shifted in such a way that it coincides with 0, thereby having no value for the threshold, which converts to this 2-parameter Weibull distribution. Okay, so now if this threshold is increased, provided beta and gamma are constant, the distribution gets stretched to the right and the height increases while maintaining its shape and location, like this graph. If eta or threshold is decreased while beta and gamma are constant, the distribution gets pushed towards the left and the height increases. So these are the various cases of the threshold. So now we come finally to the part of mathematical treatment, which has a considerable significance from the exam perspective as well. that is the mean and variance of the Weibull distribution. So particular case, first we will deal with the particular case. If beta, that is the slope parameter, is 1, then the Weibull distribution becomes identical to the exponential distribution, that is theta e to the power minus theta x. So here theta is replaced by 1 upon alpha. So this is an observation, this is an observed result, but it can prove to be significant for further proofs and further calculations. So the mean, we come back to our topic, the mean and variance of the Weibull distribution. So here we have this calculation or proof, whatever it is. So mu r dash is defined as the expectation of x to the power r, which is y to the power 1 by c whole to the power r, which is e to the power expectation of y to the power r upon c. Now we need to know that mu r dash is defined as the gamma function of r upon c plus 1. Now as per the definition of gamma function, we have gamma of z equals to the integration of e to the power minus t to the power z minus 1 dt, with the limits of integration from 0 to infinity. So using the same formula, we get mu r dash equals to integration e to the power minus y to the power r by c dy, with limits of integration from 0 to infinity. So now calculating it further, we get mean, that is expectation of x, is the gamma function of 1 by c plus 1. Now if we are supposed to calculate the variance of x, so we know that the variance of x is equals to expectation of x square minus expectation of x whole square, which is gamma function of 2 by c plus 1 minus the mean, that is the gamma function of 1 by c plus 1 whole square. Similarly, we can obtain expressions for the higher order moments, and hence for beta 1 and beta 2. For larger value of c here is a constant. The mean is approximated by expectation of x equals to 1 minus gamma upon c plus 1 upon 2c square in bracket pi square upon 6 plus gamma square. So which is equals to 1 minus 0.57722 c inverse, that is c to the power minus 1, plus 0.98905 c to the power minus 2, where this gamma equals to 0.57722 is the Euler's constant. So now, as there should be an age of technology to everything, and most of the problems which you people would be solving would be, of course, in your practicals, and there you would be required to use the softwares like Excel to solve the problems related to Weibull distribution. So we will be dealing as to how Excel functions can be used to solve the problems of Weibull distribution. So MS Excel provides the following function regarding the Weibull distribution. Weibull in bracket x, alpha, beta, cumulative, where alpha and beta are the shape and the scale parameters, x is the value at which the function is to be calculated, and cum, that is cumulative, it denotes true or false. So in case this cumulative is equals to false, so here it means that this function will calculate the value of the Weibull probability distribution function, that is PDF f of x at x. Whereas if we regard cum, that is cumulative, as true, so this function will denote the value of the Weibull cumulative distribution function, that is probability of capital X less than or equal to x of f of x at x. So I will also like to provide an illustrative example. So let's say we are now dealing with an illustrative example of solving the Weibull distribution on MS Excel. So this is the question. So the first and the primary requirement of any software for calculating anything is to first elaborate the components of the formula or that syntax very well, which are also called as the arguments of that syntax. So the first argument is Weibull, where we are supposed to calculate the Weibull distribution. X is the value at which we have to evaluate this Weibull distribution, which is a non-negative number. Alpha is the parameter of the distribution. We know what it is. So here in the context of MS Excel, we are just supposed to say that it is a positive number. The property of it being a positive number is to be defined very clearly, very succinctly. Again, beta is also a parameter of the distribution, which is a positive number. We have to again describe its positivity very clearly. And cumulative is a logical value for the cumulative distribution function. And for cumulative distribution function, we have to use true. For probability mass function, we have to use false. So here you can see that we have allotted the values for every part or every element of this function. The value of x is 110, the value of alpha is 25, the value of beta is 99, and the value of cumulative function, that is the status of cumulative function, is true. That is, we have to use the cumulative distribution function. In short, we have to find the Weibull CDF P of x less than or equal to x. So for doing so, we give this syntax equal to Weibull bracket open C4, the cell C4. As you can see, this is C, this is 4, which denotes the value of x, comma C6. As you can see, it is C6, it denotes the value of alpha, comma C8, C8, which denotes the value of beta, comma C10, which denotes the status of it being cumulative or not cumulative, which is denoted in C10. Now after describing all the parameters, we close the bracket, and as soon as we press the enter button, we get this value 0.9999108. So here 99999 denotes the PDF of the Weibull distribution given the parameters. So now I think I am done with all which I was supposed to say. So it's the time for acknowledgements. So these are all the sources which I used for designing this seminar. So I thank you for all your time and your attention. Thank you.